This heritage science book has been brought to life in audio, especially to support listeners with visual impairments. If you believe in what we're doing, please visit the YouTube description to support this work. Your help truly matters. And yes, this project uses AI, but it's AI for good. Dynamics of Rotation, Chapter 1. Definitions of terms and preliminary kinematics. Rigid body. A body in dynamics is said to be rigid, that is, stiff, so long as the forces acting upon it do not change the relative positions of its parts. We shall deal at first chiefly with such familiar rigid bodies as a flywheel turning on its axle, a cylindrical shaft, a grindstone, a door turning on its hinges, a pendulum, a magnetic compass needle, the needle of a galvanometer with its attached mirror. It should be observed that such a body as, for example, a wheelbarrow being wheeled along a road is not, taken as a whole, a rigid body, for any point on the circumference of the wheel changes its position with respect to the rest of the barrow. The wheelbarrow consists, in fact, of two practically rigid bodies, the wheel and the barrow. On the other hand, a sailing boat may be regarded as a rigid body so long as its sails are taut under the influence of the wind, even though they be made of a material that is far from rigid when otherwise handled. So also a stone whirled by an inextensible string constitutes with the string a single body which may be regarded as rigid so long as the string is straight. Angular velocity. When a rigid body turns about a fixed axis, every particle of the body describes a circle about this axis in the same time. If we conceive a radius to be drawn from the center of any such circular path to the particle describing it, then, if the rotation be uniform, the number of unit angles swept out in unit time by such a radius is the measure of what is called the angular velocity of the body, or its rotational velocity. The unit of time invariably chosen is the second, and the unit angle is the radian, that is, the angle of which the arc is equal to the radius. Hence, in brief, we may write angular velocity, when uniform, equals number of radians described per second. The usual symbol for the rotational or angular velocity of a body is omega, the Greek letter. When the rotational velocity is not uniform but varies, then its value at any instant is the number of radians that would be swept out per second if the rate of turning at that instant remained uniform for a second. Rate of revolution. Since in one revolution the radius describes 2 pi radians, it follows that the number of revolutions made per second when the angular velocity is omega divided by 2 pi. That is, when a body makes 1 revolution per second, it describes 2 pi unit angles per second and has therefore an angular velocity omega equal to 2 pi. Thus, a body which makes 20 turns a minute has an angular velocity equal to 20 divided by 60 times 2 pi, which equals 2 pi over 3 radians per second. Relation between v and omega. Since a rotational velocity omega radians per second corresponds to a travel of the particle over an arc of omega each second, it follows that v equals r times omega, or omega equals v divided by r. Very frequent use will be made of this relation. Examples. First, a rotating drum 4 feet in diameter is driven by a strap which travels 600 feet a minute and without slipping on the drum. To find the angular velocity, omega equals v divided by r, which is 600 divided by 2, equals 5 radians per second. Second, a wheel 3 feet in diameter has an angular velocity of 10. Find the speed of a point on its circumference. V equals r omega, which equals 1.5 times 10 feet per second equals 15 feet per second. Angular acceleration. When the rate of rotation of a rigid body about a fixed axle varies, then the rate of change of the angular or rotational velocity is called the angular or rotational acceleration, just as rate of change of linear velocity is called linear acceleration. The usual symbol for angular acceleration is alpha. Thus, alpha is at any instant the number of radians per second that are being added per second at the instant under consideration. We shall deal at first with uniform angular accelerations, for which we shall use the general symbol alpha. In the text, omega dot, that is, the time derivative of angular velocity, is referred to as alpha, which is the standard symbol for angular acceleration. Now, while the book occasionally adopts the letter A to stand in for this, in our narration we will always spell out alpha to remain clear, consistent, and aligned with spoken notation conventions. uniformly accelerated rotation. If a rigid body starts rotating from rest with a uniform angular acceleration alpha, then after t seconds, the angular velocity omega is given by omega equals alpha times t. If the body, instead of being at rest, had initially an angular velocity omega naught, then at the end of the interval of t seconds, the angular velocity would be omega equals omega naught plus alpha times t. This is equation 1. Since during the t seconds the velocity has grown at a uniform rate, it follows that its average value during the interval, which when multiplied by the time will give the whole angle described, lies midway between, or is the arithmetic mean between, the initial and final values. That is, the average angular velocity for the interval is omega average equals omega naught plus omega divided by 2, which equals omega naught plus 1/2 alpha t. And the angle described theta is theta equals omega naught plus 1/2 alpha t times t, or theta equals omega naught t plus 1/2 alpha t squared. This is equation 2. By substituting this value of theta into equation 1, we obtain the equation omega squared equals omega naught squared plus 2 alpha theta. This is equation 3, which connects the angular velocity omega with the initial velocity omega naught and the angle theta swept through. The student will observe that these equations are precisely similar to and are derived in precisely the same way as the 3 fundamental kinematic equations that he has learned to use in dealing with uniformly accelerated rectilinear motion of a particle, namely v equals u plus at, equation 1, s equals ut plus 1/2 at squared, equation 2, and v squared equals u squared plus 2as, equation 3. Example 1. A wheel is set gradually rotating from rest with a uniform angular acceleration of 30 units of angular velocity per second. In what time will it acquire a rate of rotation of 300 revolutions per minute? Solution. 300 revolutions per minute is an angular velocity of 300 times 2 pi divided by 60, which is 300 times 2 pi over 60 radians per second. This equals 10 pi radians per second. Now, using the equation omega equals alpha t, we write 10 pi equals 30 times t. So t equals 10 pi divided by 30. This gives t equals pi over 3 seconds, which is approximately 3.1416 over 3 equals 1.0472 seconds. Example 2. A wheel revolves 30 times per second. With what uniform angular acceleration will it come to rest in 12 seconds, and how many turns will it make in coming to rest? Solution. Initial angular velocity equals 30 times 2 pi, which equals 60 pi. This velocity is destroyed in 12 seconds. Therefore, angular acceleration equals final minus initial over time, that is 0 minus 60 pi divided by 12. That equals negative 5 pi. So angular acceleration equals negative 15.708 radians per second each second. The minus sign means that the direction of the acceleration is opposite to that of the initial velocity omega, which we have tacitly assumed to be positive in writing it equal to 60 pi. The angle described in coming to rest is obtained at once from the third of the fundamental equations now that we know the value of alpha. Thus, omega squared equals omega naught squared plus 2 alpha theta. 0 equals 60 pi squared minus 10 pi theta. That gives 10 pi theta equals 60 pi squared. So theta equals 360 pi, and theta over 2 pi equals 180 revolutions. Example 3. A wheel rotating 3,000 times a minute has a uniform angular retardation of pi radians per second each second. Find when it will be brought to rest and when it will be rotating at the same rate in the opposite direction. 3,000 revolutions per minute equals 3,000 times 2 pi over 60, which is 100 pi radians per second. This will be destroyed by the opposing acceleration pi in 100 seconds. The wheel will then be at rest, and in 100 seconds more, the same angular velocity will have been generated in the opposite direction. Compare this example with that of a stone thrown vertically up and then returning. Now we're diving into a set of examples that apply the equations of uniformly accelerated rotation. This is where the math meets motion. To follow along, remember, we're using the same trio of kinematic equations from linear motion, just reinterpreted for rotation. 1. Omega equals omega naught plus alpha t. 2. Theta equals omega naught t plus 1/2 alpha t squared. 3. Omega squared equals omega naught squared plus 2 alpha theta. Let's go. Example 1. Reaching a target rotation rate. Imagine a wheel starts from rest, that means 0 angular velocity, and it accelerates at a steady rate of 30 radians per second each second. We want to know how long it takes to reach 300 revolutions per minute. Now, pause and translate. 300 revolutions per minute is a target angular velocity. So we convert that to radians per second. 300 times 2 pi divided by 60 gives us 10 pi radians per second. We're looking for time, and we know the wheel starts from rest, so the angular velocity goes from 0 to 10 pi with a constant angular acceleration of 30. That's textbook use of equation 1. Omega equals alpha times t. We rearrange to get t equals omega over alpha. That's 10 pi over 30, which simplifies to pi over 3 seconds. And numerically, that's about 1.0472 seconds. So the key logic here, recognize you're given a final angular velocity, a starting point of rest, and a constant acceleration. You go straight to the first kinematic equation for angular motion. Example 2, coming to rest. Now flip the situation. A wheel is spinning fast, 30 revolutions per second, and we want to know what steady angular acceleration will bring it to rest in 12 seconds. And while we're at it, how many full turns does it make before stopping? Step 1. Identify your variables. Initial angular velocity, 30 revs per second, which becomes 60 pi radians per second. Final velocity, 0, since it's coming to rest. Time, 12 seconds. We're solving for alpha, the angular acceleration. So we use equation 1 again, omega equals omega naught plus alpha dt. Rearranged, alpha equals omega minus omega naught over t. Substitute 0 minus 60 pi over 12. That's negative 5 pi. The minus sign means it's slowing down. Deceleration. Next, the turns. Now we want total angle swept out, theta, before stopping. We turn to equation 3. Omega squared equals omega naught squared plus 2 alpha theta. Substitute in 0 equals 60 pi squared plus 2 times negative 5 pi times theta. Solve for theta, you'll get 360 pi. Divide by 2 pi to get revolutions. That's 180 full turns before the wheel comes to rest. The big idea, use equation 1 to find alpha, then plug that into equation 3 to get the total angular displacement. Example 3, full reversal of direction. Here's a neat one. A wheel is spinning really fast, 3,000 revolutions per minute, but it's slowing down under a steady angular deceleration, a retardation of pi radians per second squared. We're asked 2 things. 1, how long until it stops? 2, when will it be spinning at the same speed but in the opposite direction? First, translate angular velocity. 3,000 revs per minute is 100 pi radians per second, and the deceleration is pi per second squared. Stopping time is straight from equation 1, omega equals omega naught plus alpha t. We solve 0 equals 100 pi minus pi times t. That gives t equals 100 seconds. That's the moment of rest. But we're also told the acceleration continues. So in another 100 seconds, the wheel gains another 100 pi radians per second, but now in the opposite direction. Final answer, it comes to rest in 100 seconds and reverses to the same speed in another 100 seconds. Total of 200 seconds for a full reversal. Geometrical representation of rotational velocities and accelerations. At any particular instant, the motion of a rigid body with one point fixed must be one of rotation with some definite angular velocity about some axis fixed in space and passing through the point. Thus, the rotational velocity is, at any instant, completely represented by drawing a straight line of length proportional to the rotational velocity in the direction of the axis in question. And it is usual to agree that the direction of drawing and naming shall be that in which a person looking along the axis would find the rotation about it to be right-handed or clockwise. Thus, the line OA would correspond to the direction of rotation indicated in the figure. If we choose to conceive a body as affected by simultaneous component rotations about 3 rectangular intersecting axes, we shall obtain the actual axis and rotational velocity from the lines representing these components by the parallelogram law. In the same way, rotational acceleration about any axis fixed in space may be represented by drawing a line in its direction using the same convention, and simultaneous rotational accelerations may be combined according to the parallelogram law. So here's the idea. Whenever a rigid body spins around a fixed point, you can imagine that spin as happening around a specific axis at that moment. That axis might be vertical, horizontal, or at any angle, but there's always one. Now, instead of trying to picture the whole spinning object, we can represent its rotation just by drawing a line. That line shows two things. One, direction, which way the axis points. Two, length, how strong or how fast the rotation is. Longer line means faster spinning. And here's a helpful convention. If you point your right hand's thumb along that line and curl your fingers show the direction the object is spinning. That's called the right hand rule. This helps us define the positive direction for angular velocity. So in the figure they showed, the line OA points in the direction of the axis, and its length stands for how fast the object is rotating. Now, sometimes a body might be spinning around more than one axis at once. For example, imagine it wobbling while spinning. In that case, we can break the motion down into parts, like one spin around the x-axis, one around the y, and one around the z. And then we use the parallelogram law, a simple vector method, to combine those into a single total angular velocity. Same goes for angular acceleration. We can draw a line to represent it too. Same rules apply. If there are multiple accelerations acting, we can combine them using the same parallelogram approach. On the use of the word moment. The word moment was first used in mechanics in its now rather old-fashioned sense of importance or consequence. So when we speak of the moment of a force about an axis, we mean the importance of that force with respect to its power to cause rotation about the axis. And likewise, moment of inertia means the importance of a body's inertia when we try to rotate it about an axis. Now, when we say that the moment of a force about an axis varies with the force and with the distance of its line of action from the axis, we're not really defining the phrase. We're describing what experiments have shown, that forces applied farther from an axis are more effective at producing rotation. That's the heart of the idea. Moment is about turning power. And the authors emphasize students should keep this original meaning in mind, so that when you hear moment of a force or moment of inertia, you don't just think of numbers, you think of turning effect or resistance to turning. But the word moment has also been borrowed for other technical meanings. You might hear moment of mass about an axis or moment of an area with respect to a plane. These don't always come with the same physical interpretation. In those cases, the term moment needs a precise mathematical definition, and it doesn't always have the intuitive physical connection to torque or inertia. Now, torque, the modern word for turning power. To avoid confusion, the word torque is now widely used for what was once called the moment of a force. This is helpful because torque is unambiguous. It means the power of a force or system of forces to cause rotation about an axis. The word comes from the Latin torqueo, I twist. Two torques are said to be equal if they can be statically balanced by the same torque. That's the definition of equal torques. Fundamental statical experiment. If two different force setups produce the same turning effect when the product of force and its distance from the axis is the same, then those torques are equal. This is something we can verify experimentally and also derive from Newton's laws. Measure of torque. The value of torque is defined by the product of the force and the distance from the axis. And this is really a matter of agreed definition, just like defining force as mass times acceleration. Unit torque. A unit torque is when a unit force acts at a unit distance from the axis. This is the reference case, 1 unit of force, 1 unit of arm length, giving 1 unit of torque. So a force acting on any point in its plane produces a torque equal to the product of the force and its perpendicular distance to the axis. When that product equals 1, the torque is said to be 1 unit. Now let's slow it down and really unpack what torque means in a way that's clear and easy to picture. Torque is not moment times distance. Torque is the moment of a force, and that moment is defined as force multiplied by distance, specifically the perpendicular distance from the axis of rotation to the line of action of the force. So yes, torque equals force times distance. It tells us how much rotational effect a force has. Same force applied farther from the axis gives more torque, more turning power. This distance, often called the moment arm, is what makes torque so much more than just a force. It's force with leverage. Now about the units of torque. Torque is measured in Newton meters, force times distance. And wait a second, that sounds like the same unit as energy, doesn't it? Yes, numerically, the unit is the same, but conceptually they're very different. Energy is scalar. It doesn't care about direction. It's just how much work is done. Torque is a vector. It points along the axis of rotation, and its direction matters. So even though both are in Newton meters, they represent different kinds of physical quantities. Think of torque as twisting force and energy as accumulated effort. And yes, your connection to momentum is spot on. Just as linear momentum is called the quantity of motion for objects moving in straight lines, torque plays a similar role in rotational motion. It's the rotational counterpart to force. It tells us how the angular momentum of a system will change. So in short, force changes linear momentum. Torque changes angular momentum. Both are products, force times distance or mass times velocity. Chapter 2. Rotation under the influence of torque. The student will have learnt in that part of dynamics, which deals with the rectilinear motion of matter under the influence of force, and with which he is assumed to be familiar, that the fundamental laws of the subject are expressed in the three statements known as Newton's laws of motion. These propositions are the expression of experimental facts. Thus, nothing but observation or experience could tell us that the acceleration which a certain force produces in a given mass would be independent of the velocity with which the mass was already moving, or that it was not more difficult to set matter in motion in one direction in space than in another. We shall now point out that in the study of the rotational motion of a rigid body, we have exactly analogous laws and properties to deal with. Only that instead of dealing with forces, we have torques. Instead of rectilinear velocities and accelerations, we have angular velocities and accelerations. And instead of the simple inertia of the body, we have to consider the importance or moment of that inertia about the axis, which importance or moment we shall learn how to measure. It will contribute to clearness to enunciate these corresponding laws with reference first to a rigid body pivoted about a fixed axle. That is, an axis which remains fixed in the body and in its position in space. And although it is possible to deduce each of the propositions that will be enunciated as consequences of Newton's laws of motion without any further appeal to experiment, yet we shall reserve such deduction till later, and present the facts as capable, in this limited case at any rate, of fairly exact, direct experimental verification. Proposition 1. The rate of rotation of a rigid body revolving about an axis fixed in the body and in space cannot be changed except by the application of an external force having a moment about the axis, that is, by an external torque. Thus, a wheel capable of rotating about a fixed axle cannot begin rotating of itself, but if once set rotating would continue to rotate forever with the same angular velocity, unless acted on by some external torque, due, for example, to friction, having a moment about the axis. Any force whose line of action passes through the axis will, since this is fixed, be balanced by the equal and opposite pressure which fixes the axis. It is true that pressure of a rotating wheel against the material axle or shaft about which it revolves does tend to diminish the rate of rotation, but only indirectly by evoking friction which has a moment about the axis. It is impossible in practice to avoid loss of rotation through the action of friction, both with the bearings on which the body is pivoted and with the air. But since the rotation is always the more prolonged and uniform, the more this friction is diminished, it is impossible to avoid the inference that the motion would continue unaltered for an indefinite period could the friction be entirely removed. The student will perceive the analogy between this first proposition and that known as Newton's first law of motion. Proposition 2. The angular acceleration or rate of change of angular velocity produced in any given rigid mass rotating about an axis fixed in the body and in space is proportional to the moment about the axis of the external forces applied, that is, to the value of the external torque. To fix the ideas, let the student think first of a wheel rotating about a fixed shaft passing through its center, and to this wheel let us apply a constant torque by pulling with constant force the cord AB wrapped round the circumference. It may be well to point out here that if the wheel be accurately symmetrical, so that its center of gravity lies in the axis of the shaft, then, as will be shown in the chapter on the center of mass, since the Since the center of gravity or center of mass of the wheel does not move, there must be some other equal and opposite external force acting on the body. This other force is the pressure of the axle, so that we are really applying a couple, as in Figure 2. But this latter force has no moment about the axis and does not directly affect the rotation. Our proposition asserts that 1. So long as the torque has the same value, that is, so long as the cord is pulled with the same force, the acceleration of the angular velocity of the wheel is uniform, so that the effect on the wheel of any torque in adding or subtracting angular velocity is independent of the rate at which the wheel may happen to be rotating when the torque is applied. 2. That a torque of double or treble the value would produce double or treble the acceleration, and so on. 3. If several torques be applied simultaneously, the effect of each on the rotation is precisely the same as if it acted alone. Also, it follows, 4, that different torques may be compared not only statically but also dynamically by allowing them to act in turn on the same pivoted rigid body in a plane perpendicular to the axis and observing the angular velocity that each generates or destroys in the same time. Methods of experimental verification. Let an arrangement equivalent to that of the figure be made. A B is an accurately centered wheel turning with as little friction as possible on a horizontal axis, for example, a bicycle wheel on ball bearings. Round its circumference is wrapped a fine cord, from one end of which hangs a mass C of known weight, W, which descends in front of a graduated scale. It will be observed that C descends with uniform acceleration. This proves that the tension T of the cord BC on the weight is uniform, and from observation of the value A of the acceleration, that of the tension is easily found, being given by the relation W minus T equals A over G, where G is the acceleration that would be produced in the mass by the force W alone, and T multiplied by the radius of the wheel is the measure of the torque exerted. Thus, the arrangement enables us to apply a known and constant torque. But since the linear acceleration of C is uniform, it follows that the angular acceleration of the wheel is uniform. By varying the weight W, the torque may be varied, and other torques may be applied simultaneously by means of weights hung over the axle or over a drum attached thereto, and thus the proportionality of angular acceleration to total resultant torque tested under various conditions. It will be observed that in the experiments described, we assume the truth of Newton's second law of motion in order to determine the value of the tension T of the cord. But it is possible to determine this directly by inserting between C and B a light spring, whose elongation during the descent tells us the tension applied without any such assumption. Instead of using our known torque to generate angular velocity from rest, we may employ it to destroy angular velocity already existing in the following manner. Let a massive flywheel or disk be set rotating about an axis with a given angular velocity, and be brought to rest by a friction brake which may be easily controlled so as to maintain a constant, measurable retarding torque. It will be found that, however fast or slowly the wheel be rotating, the same amount of angular velocity is destroyed in the same time by the same retarding torque. That a torque n times as great destroys the same amount of angular velocity in 1 over n of the time, while if a second brake be applied simultaneously, the effect of its retarding couple is simply superadded to that of the first. It may be remarked that the direct experimental verifications here quoted can be performed with probably greater accuracy than any equally direct experiment on that part of Newton's second law of motion to which our second proposition corresponds, viz., that the linear acceleration of a given body is proportional to the impressed force and takes place in the direction of the force. Thus, our second proposition for rotational motion is really less far removed than is Newton's second law of motion from fundamental experiment. Familiar instances. Most people are quite familiar with immediate consequences of these principles. For example, in order to close a door, everyone takes care to apply pressure near the outer and not near the hinged side, so as to secure a greater moment for the force. A workman checking the rotation of any small wheel by friction of the hand applies his hand near the circumference, not near the axis, the analog of mass in rotational motion. In the study of rectilinear motion, it is found that if after making experiments on some given body, we pass to another, The same forces applied to the second body do not, in general, produce in it the same accelerations. The second body is found to be less easy or more easy to accelerate than the first. We express this fact by saying that the inertia or mass of the second body is greater or less than that of the first. Exactly the same thing occurs in the case of rotational motion, for experiment shows that the same torque applied to different rigid bodies for the same time produces, in general, different changes of angular velocity. Thus, the pull of a cord wrapped round the axle of a massive flywheel will, in say 10 seconds, produce only a very slow rotation, while the same torque applied to a smaller and lighter wheel will, in the same time, communicate a much greater angular velocity. It is found, however, that the time required for a given torque to produce a given angular velocity does not depend simply on the mass of the rigid body. For if the wheel be provided, as in the figure, with heavy bosses, and these be moved further from the axis, then, although the mass or inertia of the wheel, as regards bodily motion of the whole in a straight line, is unaltered, yet it is now found to be more difficult to accelerate rotationally than before. The experiment may be easily made with our bicycle wheel of figure 4 by removing alternate tensional spokes and fitting it with others to which sliding masses can be conveniently attached. With two wheels, however, or other rigid bodies, precisely similar in all respects except that one is made of a lighter material than the other, so that the masses are different, it is found that the one of less mass is proportionately more easy to accelerate rotationally. Hence, we perceive that in studying rotational motion, we have to deal not only with the quantity of matter in the body, but also with the arrangement of this matter about the axis. Not solely with the mass or inertia of the body, but with the importance or moment of this inertia with respect to the axis in question. We shall speak of this for the present as the rotational inertia of the body, meaning that property of the body which determines the time required for a given torque to create or destroy in the body a given amount of rotational velocity about the axis in question. Definition of the unit of rotational inertia. Just as in the dynamics of rectilinear motion, we may agree that a body shall be said to have unit mass when unit force acting on it produces unit acceleration. So in dealing with the rotation of a rigid body, it is agreed to say that the body has unit rotational inertia about the axis in question when unit torque gives it unit angular acceleration, that is, adds or destroys in it in 1 second an angular velocity of 1 radian per sec. If unit torque acting on the body takes not 1 second, but 2 to generate the unit angular velocity, then we say that the rotational inertia of the body is 2 units. And speaking generally, the relation between the torque which acts the rotational inertia of the body acted on and the angular acceleration produced is given by the equation. Angular acceleration equals torque divided by rotational inertia. Just as in rectilinear motion, the impressed force, the mass acted on, and the linear acceleration produced are connected by the relation acceleration equals force divided by mass. Examples for solution. 1. A friction brake which exerts a constant friction of 200 pounds at a distance of 9 inches from the axis of a flywheel rotating 90 times a minute brings it to rest in 30 seconds. Compare the rotational inertia of this wheel with one whose rate of rotation is reduced from 100 to 70 turns per minute by a friction couple of 80 pound-foot units in 18 seconds. Answer: 25 to 24. 2. A cord is wrapped around the axle 8 inches in diameter of a massive wheel whose rotational inertia is 200 units and is pulled with a constant force of 20 units for 15 seconds when it comes off. What will then be the rate of revolution of the wheel in turns per minute? The unit of length being 1 foot and of time 1 second. Answer: 4.774 turns per minute. To calculate the rotational inertia of any rigid body, we shall now show how the rotational inertia of any rigid body may be calculated when the arrangement of its particles is known. We premise first the following. Proposition 3. The rotational inertia of any rigid body is the sum of the rotational inertias of its constituent parts. That this is true may be accurately ascertained by trials with the experimental wheel of figures 4 and 5. Let the wheel, unloaded by any sliding pieces, have its rotational inertia determined by experiment with a known torque in the manner already indicated, and call its value I0. Then let sliding pieces be attached in certain noticed positions, and let the new value of the rotational inertia be I1. Then, according to our proposition, I1 minus I0 is the rotational inertia of the sliders. If this be the case, then the increase of rotational inertia produced by the sliders in this position should be the same, whether the wheel be previously loaded or not. If trial be now made with the wheel loaded in all sorts of ways, it will be found that this is the case. The addition of the sliders in the noticed positions always contributes the same increase to the rotational inertia. Rotational inertia of an ideal single particle system. We now proceed to consider theoretically, in the light of our knowledge of the dynamics of a particle, what must be the rotational inertia of an ideal rigid system consisting of a single particle of mass m, connected by a rigid bar whose mass may be neglected to an axis at distance r. Let O be the axis, m the particle, so that OM equals r, and let the system be acted on by a torque of L units. This we may suppose to be due to a force P acting on the particle itself and always at right angles to the rod OM, and of such value that the moment of P is equal to the torque, that is, P times R equals L, or P equals L over R. The force P acting on the mass m generates in it a linear acceleration A equals P over m in its own direction. P over m is therefore the amount of linear speed generated per unit time by the force in its own direction, and whatever be the variations in this linear speed v, v over r is always equal to the rotational velocity omega, and therefore the amount of rotational velocity generated per unit time, or the rotational acceleration A, is 1 over rth of the linear speed generated in the same time. That is, A equals P over mr equals P over mr squared equals L lover mr squared equals torque over mr squared. But A equals torque divided by rotational inertia. See page 17. Therefore, the rotational inertia of a single particle of mass m at a distance r from the axis equals mr squared. Any rigid body may be regarded as made up of such ideal single particle systems, and since the rotational inertia of the whole is the sum of the rotational inertias of the parts, we see that if m1, m2, m3, and so on be the masses of the respective particles r1, r2, r3, and so on, their distances from the axis, then the rotational inertia of the body equals m1r1 squared plus m2r2 squared plus m3r3 squared and so on equals the sum of mr squared. This quantity, the sum of mr squared, is generally called the moment of inertia of the body. The student will now understand at once why such a name should be given to it, and the name should always remind him of the experimental properties to which it refers. We shall from this point onward drop the term rotational inertia and use instead the more usual term moment of inertia, for which the customary symbol is the letter I. We now see that a particle of unit mass at unit distance from the axis has unit moment of inertia. It is evident also that a thin circular hoop of unit radius and of unit mass rotating about a central axis perpendicular to the plane of the circle has also unit moment of inertia, for every particle may with close approximation be regarded as at unit distance from the center. In fact, I equals the sum of mr squared equals the sum of m times 1 squared equals the sum of m equals 1. The same is true for any segment of a thin hoop, figure 8, of unit radius and unit mass, and it is also true for any thin hollow cylinder of unit radius and unit mass, rotating about its own axis. Thus, the student will find it an easy matter to prepare accurate standards of unit moment of inertia. A thin cylinder or hoop of 1 foot radius and weighing 1 pound will have the unit moment of inertia on the British absolute system. We shall call this the pound-foot squared unit. The engineer's unit is that of 1 slug, or 32.2 pounds, at the distance of 1 foot, that is a slug foot squared. Definition of angular momentum. Just as the product mass times velocity, or mv in translational motion, is called momentum, so by analogy, when a rigid body rotates about a fixed axle, the product moment of inertia times angular or rotational velocity, or I omega, is called angular or rotational momentum. And just as a force is measured by the change of momentum it produces in unit time, so a torque of about any axis is measured by the change of angular momentum it produces in unit time in a rigid body pivoted about that axis. For since A equals torque divided by I, therefore L equals IA. To find the kinetic energy of a rigid body rotating about a fixed axle. At any given instant, every particle is moving in the direction of the tangent to its circular path with a speed v, and its kinetic energy is therefore equivalent to 1/2 mv squared units of work. And since this is true for all the particles, the kinetic energy may be written the sum of mv squared over 2. But for any particle, the tangential speed v equals r omega, where r is the distance of the particle from the axis and omega is the angular velocity. Therefore, kinetic energy equals 1/2 mr squared omega squared units of work. And in a rigid body, omega is the same for every particle. Therefore, the kinetic energy equals 1/2 omega squared times the sum of mr squared units of work equals 1/2 I omega squared units of work. The student will observe that this expression is exactly analogous to the corresponding expression 1/2 mv squared for the kinetic energy of translation. Work done by a couple. When a couple in a plane at right angles to the fixed axis about which a rigid body is pivoted turns the body through an angle theta, the moment of the couple retaining the same value L during the rotation, then the work done by the couple is L theta. For the couple is equivalent in its effect on the rotation to a single force of magnitude L, acting at unit distance from the axis, and always at right angles to the same radius during the rotation. In describing the unit angle, or 1 radian, this force advances its point of application through unit distance along the arc of the circle, and therefore does L units of work, and in describing an angle theta, does L theta units of work. The equation starts with A equals L over I. That is, angular acceleration equals torque divided by moment of inertia. This is the rotational analog of Newton's second law in linear motion. Acceleration equals force divided by mass. In rotation, L is the torque, the rotational equivalent of force. I is the moment of inertia, how much the body resists changes in its rotational motion. A is the angular acceleration, how quickly the angular velocity changes. Now, if A equals L over I, we can multiply both sides by I to isolate L. That gives L equals I times A. So the torque needed to produce a given angular acceleration depends directly on how large the moment of inertia is. If the body is harder to rotate, that is, has more moment of inertia, you need more torque to get the same angular acceleration. This equation, L equals IA, is the rotational form of Newton's second law, and it's fundamental in dynamics involving rotation. Work done by a couple. When a couple in a plane at right angles to the fixed axis about which a rigid body is pivoted turns the body through an angle theta, the moment of the couple retaining the same value L during the rotation, then the work done by the couple is L theta. For the couple is equivalent in its effect on the rotation to a single force of magnitude L, acting at unit distance from the axis and always at right angles to the same radius during the rotation. In describing the unit angle, or 1 radian, this force advances its point of application through unit distance along the arc of the circle and therefore does L units of work. And in describing an angle theta, it does L theta units of work. Analogy with the expression for the work done by a force in rectilinear motion. It will be observed that this expression for the measure of the work done by a couple is exactly analogous to that for the work done by a force in rectilinear motion. For this is measured by the product of the force and the distance through which it acts, measured in the direction of the force. If the couple be L poundal foot units, then the work done in turning through an angle theta is L theta foot poundals. If the couple be L pound-foot units, then the work done will be L theta foot-pounds. Change of kinetic energy due to a couple. When the body on which the couple acts is perfectly free to turn about a fixed axis perpendicular to the plane of the couple, it is easy to see that the work done by the couple is equal to the change in the kinetic energy of rotation. For if A be the angular acceleration, omega the initial, and omega prime the final value of the angular velocity, then see equation 3 on page 4. Omega prime squared equals omega squared plus 2a theta. Therefore, theta equals omega prime squared minus omega squared, all divided by 2a. And since a equals L over I, that is torque over moment of inertia, it follows. L theta equals 1/2 I omega prime squared minus 1/2 I omega squared. That is final kinetic energy minus initial kinetic energy. Now introducing the radius of gyration. It is evident that if we could condense the whole of the matter in a body into a single particle, there would always be some distance k from the axis at which, if the particle were placed, it would have the same moment of inertia as the body has. This distance is called the radius of gyration of the body with respect to the axis in question. It is defined by the relation capital Mk squared equals the sum over all particles of mr squared. Therefore, k squared equals the sum of mr squared over m, which is the same as the sum of r squared divided by the number of particles. In other words, k squared is the average value of the square of the distances from the axis to the several constituent equal particles of the rigid body. In a few cases, such as those of the thin hoops or thin hollow cylinder figured on page 21, the value of the radius of gyration is obvious from simple inspection, being equal to the radius of the hoop or cylinder. This is approximately true also for a flywheel of which the mass of the spokes may be neglected in comparison with that of the rim, and in which the width of the rim in the direction of a radius is small compared to the radius itself. And now, numerical examples. Note to Chapter 2. In order to bring the substance of this chapter with greater vividness and reality before the mind of the student, we have preferred to take it as a matter of observation and experiment that the power of a force to produce angular acceleration in a rigid body pivoted about a fixed axle is proportional to the product of the force and its distance from the axis, that is, to its moment in the technical sense. But this result, together with the fact that what we termed the rotational inertia of a body is given by the sum of mr squared, might have been obtained as a direct deduction from Newton's laws of motion. We now give this deduction, premising first a statement of D'Alembert's principle, which may be enunciated as follows. In considering the resultant mass acceleration produced in any direction in the particles of any material system, it is only necessary to consider the values of the external forces acting on the system. For every force is to be measured by the mass acceleration it produces in its own direction, Newton's second law of motion, and also every force acts between two portions of matter and is accompanied by equal and opposite reaction, producing an equal and opposite mass acceleration, Newton's third law. The action and reaction constitute what we call a stress. When the two portions of matter, between which a stress acts, are themselves parts of the system, it follows that the resultant mass acceleration thereby produced in the system is zero. The stress is in this case called an internal stress, and the two forces internal forces. But though the forces are internal to the system, yet they are external, as Newton called them, impressed forces on the two particles respectively. Hence, considering Newton's second law of motion to be recorded solely by observations on particles of matter, we may count up the forces acting in any direction on any material system and write them equal to the sum of the mass accelerations in the same direction. But in doing so, we ought, in the first instance at any rate, to include these internal forces. Thus, the sum of external forces in any direction plus the sum of internal forces in the same direction equals the sum of mass accelerations in the same direction. We now see that the sum of internal forces equals zero. Hence, we obtain as a deduction the sum of external forces in any direction equals the sum of mass accelerations in the same direction. Or simply, the sum of E equals the sum of ma. This justifies the extension of Newton's law from particles to bodies or systems of particles. If any forces whatever act on a free rigid body, then whether the body is thereby caused to rotate or not, the sum of the mass accelerations in any direction is equal to the sum of the resultants of the applied forces in the same direction. Now, since the line of the action of a force on a particle is the same as the line of the mass acceleration, we may multiply both the force and the mass acceleration by the distance r of this line from the axis, and thus write: the moment about any axis of the force on any particle along any line equals the moment of the mass acceleration along that line of the same particle. And therefore, summing up the results for all the particles of any system, we have The sum of moments about any axis of all the forces acting on the particles of the system equals the sum of moments about the same axis of the mass accelerations of the particles. Or, the sum of moments of the external forces plus the sum of moments of the internal forces equals the sum of moments of the mass accelerations. Now, not only are the two forces of an internal stress between two particles equal and opposite, but they are along the same straight line, and hence have equal and opposite moments about any axis whatever. Hence, the second term on the left side of the above equation is always 0, and we are left with the sum of moments of the external forces equals the sum of moments of the mass accelerations. Now, we may resolve the acceleration of any particle into three rectangular components: one along the radius drawn from the particle perpendicular to the axis, one parallel to the axis, and one perpendicular to these two. It is only the latter component, which we will call tangential, that has any moment about the axis in question, and its moment is mRa theta, where r is the length of the radius. Thus, the moment of the mass acceleration of any particle of mass m may be written mRa theta. Now, in the case of a particle which always retains the same distance r from the axis, a theta is the rate of increase of the tangential speed v, and if omega be the angular velocity about the axis, v equals r omega. So a theta equals rate of increase of omega. Also, r being constant, the rate of increase of r omega is r times the rate of increase of omega. Hence, in this case, a theta equals r times alpha, and if further the whole system consists of particles so moving and with the same angular velocity, that is, if it is a rigid body rotating about a fixed axle, then for such a body so moving, the sum of moments of the mass accelerations equals the sum of mr squared alpha. Hence, in this case, the sum of moments of the external forces equals angular acceleration times the sum of mr squared. Or the angular acceleration equals external torque divided by the sum of mr squared. Chapter 3. Definitions, axioms, and elementary theorems necessary for dealing with moments of inertia. Routh's rule and its application. Constant use will be made of the following definitions and propositions. Definition. By a slight extension of language, we speak of the moment of inertia of a given area with respect to any axis, meaning the moment of inertia which the figure would have if cut out of an indefinitely thin, perfectly uniform rigid material of unit mass per unit area, so that the mass of the figure is numerically equal to its area. This dynamical definition then becomes purely geometrical. If we say that the moment of inertia with respect to any axis of an area A, and of which the indefinitely small parts A1, A2, A3, and so on, are at distances R1, R2, R3, and so on, from the axis is equal to a 1R1 squared plus a 2R2 squared plus a 3R3 squared, and so on. Or, more compactly, A equals summation of R squared. It will be observed that the area may be either plane or curved. Definition. In the same way, the moment of inertia about any axis of any solid figure or volume V, of which V1, V2, and so on are the indefinitely small constituent parts, may be defined as V1R1 squared plus V2R2 squared plus equals the summation of VR squared. Axiom. The moment of inertia of a body with respect to any axis is the sum of the moments of inertia of any constituent parts into which we may conceive it divided, and similarly the moment of inertia with respect to any axis of any given surface or volume is equal to the sum of the moments of inertia of any constituent parts into which we may conceive the surface or volume divided. This follows from the definitions just given. Illustration. Thus, the moment of inertia of a peg top shaped as in the figure about its axis of revolution is equal to the moment of inertia of the hemispherical dome of wood ABC plus that of the conical frustum ABDE plus that of the conical point of steel DE. Axiom. It is evident that the radius of gyration of any right prism of uniform density about any axis perpendicular to its base is the same as that of the base. For we may conceive the solid divided by an indefinite number of parallel planes into thin slices, each of the same shape as the base. Thus, if k be the radius of gyration of the basal figure, and m the mass of the prism, the moment of inertia is mk squared units, and this holds whether the axis cuts the figure as OO prime or does not cut it as O1O1 prime. Thus, the problem of finding the moment of inertia of an ordinary lozenge-shaped compass needle, such as that figured, reduces to that of finding the radius of gyration about OO prime of the horizontal cross-section ABCD. Proposition 1. The moment of inertia of a lamina about any axis OZ perpendicular to its plane is equal to the sum of its moments of inertia about any two rectangular axes OX and OY in its plane, and intersecting at the point O where the axis OZ meets the plane of the lamina. Or, in an obvious notation, IZ equals IX plus IY. Proof. From the figure we have at once, IZ equals summation of MR squared equals summation of M times quantity X squared plus Y squared equals summation of MX squared plus summation of MY squared, which equals IX plus IY. Now, continuing with the example and Routh's rule for moment of inertia, we begin with the following. Example. We have already seen that a thin hoop of radius r and mass m has a moment of inertia mr squared about a central axis perpendicular to its plane. Let capital I be its moment of inertia about a diameter. Then capital I is also its moment of inertia about a second diameter perpendicular to the former. Therefore, by this proposition, 2 times capital I equals mr squared. Therefore, capital I equals mr squared over 2. That is, the moment of inertia of a hoop about a diameter is only half that about a central axis perpendicular to the plane of the hoop. Now we proceed to Routh's rule for finding the moment of inertia about an axis of symmetry in certain cases. When the axis about which the moment of inertia is required passes through the center of figure of the body and is also an axis of symmetry, then the value of the moment of inertia in a large number of simple cases is given by the following rule of Dr. Routh. Moment of inertia about an axis of symmetry equals mass multiplied by the sum of the squares of the perpendicular semi-axes divided by 3 or 4 or 5. Or alternatively, k squared equals the sum of the squares of the perpendicular semi-axes divided by 3, 4, or 5. The denominator is to be 3, 4, or 5 according as the body is a rectangle, an ellipse, including a circle, or an ellipsoid, including a sphere. This rule is simply a convenient summary of the results obtained by calculation. The calculation of the quantity summation of mr squared is, in any particular case, most readily performed by the process of integration, but the result may also be obtained in some cases by simple geometry. We give in Chapter 4 examples of the calculation in separate cases, and it will be seen that they are all rightly summarized by the rule as given. 1. Examples of the application of Dr. Routh's rule to find the radius of gyration in the following cases. Case 1 of a rectangle of sides 2a and 2b about a central axis perpendicular to its plane. Here, the semi-axes perpendicular to each other and to the axis in question are a and b. Therefore, applying the rule, we have k squared equals a squared plus b squared divided by 3. Case 2 of the same rectangle about a central axis in its plane perpendicular to one side, side b. Here the semi-axes perpendicular to each other and to the axis in question are b and 0, as shown in figure 17, since the figure has no dimensions perpendicular to its own plane. So again, k squared equals b squared plus 0 squared divided by 3, that is b squared over 3. Case 3, of a circular area of radius r about a central axis perpendicular to its plane. Here the semi-axes perpendicular to each other and to the axis of symmetry in question are r and r. Applying Routh's rule, we get k squared equals r squared plus r squared over 4, which simplifies to r squared over 2. Case 4, of a circular area about a central axis in the plane of the circle. The semi-axes, perpendicular to each other and to the axis in question, are r and 0. So applying Routh's rule again, we get k squared equals r squared plus 0 squared over 4, which is r squared over 4. Case 5, of a uniform sphere about any central axis. Here, k squared equals r squared plus r squared over 5, or 2/5 r squared. Case 6, the moment of inertia of a uniform thin rod about a central axis perpendicular to its length. Here, I equals mass times the quantity r squared plus 0 squared divided by 3. So, moment of inertia I equals mass times r squared over 3. Now, theorem of parallel axes. When the moment of inertia of any body about an axis through the center of mass, coincident with the center of gravity, is known, its moment of inertia about any parallel axis can be found by applying the following proposition. Proposition 2. The moment of inertia of any body about any axis is equal to its moment of inertia about a parallel axis through its center of mass, plus the moment of inertia which the body would have about the given axis if all collected at its center of mass. Thus, if capital I be the moment of inertia about the given axis, I naught that about the parallel axis through the center of mass, capital R the distance of the center of gravity from the given axis, and capital M the mass of the body, then the moment of inertia is given by I equals I naught plus mr squared. Let the axis of rotation cut the plane of the diagram in capital O, and let a parallel axis through the center of mass or center of gravity of the body cut the same plane in capital G. Let capital P be the projection on this plane of any particle of the body. Let little m be the mass of the particle. Now OP and GP are projections of the radii from the two axes respectively. Let PN be perpendicular to OG. Then, using the geometric identity, OP squared equals OG squared plus GP squared minus 2 OGGN. Therefore, summing over all particles, summation of MOP squared equals summation of MOG squared plus summation of MGP squared minus 2OG times summation of MGN. This gives M times OG squared plus summation of MGP squared minus 0, since G is the projection of the center of mass. The positive and negative contributions in the summation of MGN cancel each other. The body would in fact balance about any line through G. Thus, finally, the moment of inertia, I equals mr squared plus I naught, We are now in the section titled Applications, where we apply the previous results to specific geometric cases. Starting with number 1, to find the moment of inertia of a door about its hinges. We treat the door as a uniform thin lamina of breadth A and mass m. The goal is to find the moment of inertia about a vertical axis at the edge, that is, where the hinges are. We begin with the moment of inertia about a parallel axis that passes through the center of gravity. That is given by the formula I sub g equals m times the quantity a over 2 squared divided by 3. So that gives I sub g equals ma squared over 12. Now we apply the parallel axis theorem, which tells us I equals I sub g plus m times the square of the distance between the two axes. That's over 2 squared again. So I equals m squared over 12 plus m squared over 4. Combining those, I equals ms squared over 3. This is the moment of inertia of a door about its hinges. Moving to number 2. To find the moment of inertia of a uniform circular disk about a tangent in its plane. Using Routh's rule, we know the moment of inertia about the axis through the center of mass is I sub g equals mr squared plus 0, all divided by 4. So I sub g equals mr squared over 4. Then, again using the parallel axis theorem, I equals I sub g plus mr squared. So we add mr squared over 4 plus mr squared equals m times 5 r squared over 4. So the result is I equals m times 5r squared over 4. And now number 3, to find the moment of inertia of a uniform bar or prism about a central axis perpendicular to its length, where the bar is not thin. A typical example is given, a bar magnet of circular cross-section suspended by a thread. To handle such a situation, we're going to prove a new result, proposition 3. The proposition says the moment of inertia of any uniform right prism of any cross-section about a central axis perpendicular to its length is equal to the moment of inertia of the same prism as a thin bar plus the moment of inertia that the prism would have if all its mass were condensed into a single thin slice at the axis. We now move to the proof. Let G and G sub 1 be the centers of gravity of the two ends of the prism. Now we imagine the prism sliced into many elementary thin slices, all parallel to the ends. This means that each slice has the same shape and the same cross-sectional center of gravity lies along the line joining G and G sub 1. Call that the axis of the prism. Let r be the distance of any slice from the central slice and m its mass. Then by the parallel axis theorem, the moment of inertia of this slice about the central axis is I equals I sub I plus mr squared, where I sub I is the moment of inertia of that slice about an axis through its own center of mass. To get the total moment of inertia of the whole prism, we sum over all the slices. I equals the sum of I sub I plus the sum of mr squared. But the first part, the sum of the I sub I, is just the moment of inertia of all the slices gathered at the central section. So this proves the proposition. And a final note, this result is useful in analyzing systems like bar magnets oscillating in the Earth's magnetic field, where the prism is not thin and its rotation must be accurately modeled.